Welcome everybody, and thank you for joining our webinar today on vibration criteria, also known as VC curves. I'm Aidan Hubbard, I'm the sales director here at Svantek UK and Axoff Limited, and I know you're all sitting there wondering, why have we chosen VC curves as a subject for this webinar? Well, firstly, we have noticed an increase in inquiries based on VC type specifications. Maybe there's an increase in construction, maybe it's HS2. Well, in fact, we know that HS2 alone is ramping up specification and requirements for this type of monitoring. They're creating a hell of a lot of vibration. Buildings such as hospitals and universities are out there and they're all being passed by new railway tracks, and they need protection for their sensitive equipment. Equipment such as mass spectrometers and microscopes are all at risk. We're instrumentation engineers here at Svantek, and we wanted to discuss a subject that is both challenging to hardware and consultants alike. The challenge of monitoring vibration over a spectrum with multiple tolerances and alarm points, being able to report on that and being able to monitor it live in the cloud is a new and exciting way of working with VC. We do have a new vibration system, it's called the 803, and we released it a few weeks ago, and this webinar is just part of the launch campaign that we've got for this new product. Applications that require VC curves is a perfect example of how consultants and instrumentation comes together to create information that can make massive changes to building design and allows for clear and accurate advice, typically delivered by consultants. This webinar is educational, and it's why we've chosen two of the best people in the industry to discuss this with you today. So firstly, I'd like to introduce Martin McNulty, our guest expert speaker. Martin is a vibration group leader and associate director at Hawley Consultancy based in Manchester, although this role sees Martin traveling all over the country with his team. Martin will be giving us a quick talk on his experience using VC curves in the real world today. I personally see Martin as a vibration master, although he's very humble with that. He is highly renowned by his peers in acoustics, and we're very lucky to have Martin with us today. So thank you, Martin. And I'd also like to introduce Adam Marchak. Adam has been with Svantek now for a number of years and helps run the sales team globally from Warsaw in Poland. He's the Associate Sales Director for Global Sales and is a lead in instrumentation development. With a mixed background in acoustic consultancy and application engineering, means he's the perfect person to discuss the topic of VC curves with us today. Adam will know that running a global sales force allows you to fully understand the issues that are faced around the world with monitoring. And it allows you to build a huge knowledge of problem-solving techniques and how instrumentation, just like the 803, can make your life just that little bit easier. So without further ado, I'll hand over to you, Mr. Marchak.
Well, thank you very much, Aidan. That was an amazing introduction. I rarely get rattled for things like this, but you have set the bar high. So I will try to ensure that my presentation now will not lower it too much. So thank you very much again, and welcome all of you that have joined us today for our presentation on VC curves. We're planning to be able to wrap this up in about 45 minutes from now. So the agenda is now visible on your screens. After this introduction, we're going to be talking a little bit about the VC curves origin story. We want to talk about why that was developed, what it is, the actual physical quantities that we do measure before we start talking a little bit about the applications. We will look at an application scenario. In the US, we will talk about instrumentation requirements because that's what the manufacturers of instrumentation talk about. Before I'll let Martin to talk about the VC curves in practice, which I think is going to give you guys a great insight into how you can actually apply these requirements when doing design and vibration control. So, understanding vibration criterion, what it is, why we do it, why do we bother? So before we jump into all of that, it is important to understand why was it really developed. So the VC criteria were developed in the 1980s by Eric Ungar and Colin Gordon. It emerged as a response to the increasing demand for industry with stringent vibration exposure requirements. So it was originally developed for the semiconductor industry, but the VC curve quickly gained recognition and was adopted in other fields, including microelectronics, optoelectronics, and the medical industry. So Colin Gordon, who was kind of the starting point for the VC curves. That was an engineer. He worked within engineering, but also a researcher. He saw in that time when there was a rise of those industries with very vibration sensitive equipment, that we lacked the understanding of the requirements that we need to set on our buildings, on our design, on our vibration control systems. We lacked understanding on how we can do that in a good way to ensure that these very vibration sensitive facilities are not affected negatively. Okay, so he was the first to develop it, and he started doing that for the semiconductor business, but not exclusively. Now, how were those VC curves developed? In this slide, I'm showing you the study of Amick and Bu, who are two engineers or researchers that worked very closely in methodology to what Colin Gordon did. They looked at microscopes for semiconductor inspections. They looked at microscopes for semiconductor inspections that had enhancement up to 1,000. So now imagine you're holding your phone, you want to take a picture of something. You want to take a picture of something, but it's cold outside. Your hands are shaking. Your hands are shaking, and thus the picture becomes blurry. You can't really see what you took a picture of. Now imagine that same scenario, but times 1,000. Okay, so in their study, they were looking at these different microscopes. They were looking at vibration amplitudes that were far below the threshold of what we can actually sense of our perception. We cannot sense these vibrations. If I put my hand on the table that is vibrating with 100 micrometers per second, I will not sense that, but the equipment will. And what they found is that it was not simply the amplitude. It was not simply the amplitude of vibrations that could cause this blurriness, that could cause the quality of the image to become poor. It was also vibration dependent. So they start looking at curves. They start looking at curves as the one presented here. And this is very close to what Colin Gordon did. So Colin Gordon developed the VC curves as shown on your screen right now as a frequency dependent threshold, a vibration criteria that you need to upfill when creating a space, when creating a laboratory, or creating a manufacturing site. You need to upfill these criterions in order to be able to ensure that the space you created will be able to perform that operation without any negative impact. Initially, VCA to VCD curves were introduced. However, they were quickly followed up with the ISO requirements for human exposure to vibration, which could also be measured and compared to similarly. So anything above operating theater in this picture right here, that is something that we can sense. And in order to help us understand that, these different VC curves, these different requirements, they also created a general description of applications and interpretations. So just to very quickly go through this, a workshop curve that we saw in the previous picture, right? The workshop curve here, which lies around 1,000 micrometers per second. That is an appropriate vibration level for a non-sensitive area, such as a workshop. However, if you're working in a hospital and you want to perform MRI measurements, then you should go to VCA. And reading through this table, we could get a better understanding. So we don't only look at the levels, but we also look at the appropriate assignments. Now, please take a look at VCG to VCE. These are very challenging criteria to achieve. Already when we're talking about VC curves, something that needs to be stated because I know that we have a mixed audience. When we talk about VC curves, we're talking about vibration levels that are so low that you can't really feel them. We're not longer talking about vibration levels that can be a threat to the structural integrity of a building or a bridge. We're not talking about vibrations that will have a negative effect on the human being if he lives in an area with that kind of vibration, such as VDV. We're talking about vibration levels that are to be applied on the most sensitive equipment. So just with the base on these few slides that we have gone through, you might already feel sort of secure when it comes to the vibration curves, VC curves, vibration criterion curves. Now, so did we here at Svantek. So when we were doing our research, when we're applying these in our instruments, we're applying these in our softwares and our standards here internally at Svantek, we quickly noticed that there is some confusion surrounding the VC curves. As you can see here on this slide, I have 4 slides of something that potentially is the same thing, VC curves, but they're all looking differently. The figure on the left is all curved all the way to VCE, while the figure in the middle generated in Excel shows that the VCA curve needs to be flat. We also have our initial figure here on the right, which shows VCC as a flat curve and everything above that as a curved one. So which one is it? Which one should we be applying? You know what? We went to the source. We went to Colin Gordon Associates and we simply asked, what is the current VC curve that we should be looking at when we're talking about VC curves? And their response was simple. This is the most up-to-date one. This is the one you should be applying. However, there is a but, and this but I need to walk you through, because why wouldn't you be able to use this one that you were looking at before? Well, let me walk you through this. When these VC curves were established in the beginning, we had limited abilities when it comes to vibration control. Since then, vibration control and vibration dampers have gone a long way, allowing us to create vibration-free environments in noisy areas, all right? Noisy, not necessarily acoustical noise, but also the vibration magnitudes. So if you were working in an environment where there were a lot of heavy equipment, machinery, street traffic, you name it, you could find yourself in a very high vibrating environment, not allowing you to perform these very fine operations that we talked about. However, with the development of advanced pneumatic vibration dampers, we're able to create things such as tables that were completely separated, decoupled by vibration from the area. And then if you would measure the VC or the vibration level using the VC criterions on these tables, if you had what we showed here, a curved VC curve, you could say, well, I'm doing VCC, it's all great. Something to remember with these pneumatic systems is that they introduce or could introduce a low frequency resonance. We're using soft springs, and they may even amplify those low frequency vibrations. Therefore, there was an update to the VC curves. And we need to think about that VC curves. This is not an internationally or nationally standardized standard. It is a best practice developed by some of the finest researchers within the vibration field. But it is still a baseline criterion that we can update to make it remain relevant. And as you can see in the figure right here, there was the ability to update the VC curves that if you're using low frequency pneumatic insulation in your vibration control strategy, you might want to be looking at all the way to 1 Hertz when it comes to vibration curves. Now remember again, I'm going to show this here. For example, the VCA curve, that is something that goes from 4 to 8 Hertz when it comes to that curve, and then it operates flat all the way to 80 Hertz. Now, if you will have a scenario where there is a pneumatic insulation on the flooring, then you might want to think of making it flat all the way to 1 Hertz to ensure that through this you have not introduced another vibration level in the low frequency field where you were not expecting anything. And the conclusion here when it comes to the confusion surrounding VC curves is that VC curves can be both curved or flat. It is not a single use system where you will always think VCC is this and it is this and only this. You need to be considering the use of vibration control, and you need to be considering that when you perform your measurement analysis. And you also need to consider this when defining what kind of hardware you want to use for the measurement, because you need to be able to define these both flat and curved lines within the measurement device to be able to get the highest level of analysis possible. With that being said, I still keep to what we were told by the Colin Gordon associates, that the one shown on the right here is the one that is the most up to date. And in order to conclude this first background part of this presentation, the vibration thresholds have since been applied in other industries and other applications. As we mentioned in the initial slide, when Colin Gordon did this in the beginning, he defined VCA to VCE, and that was it. Since then, we have had even lower requirements, even lower vibration levels are required within the laser and optical systems, micro nano industries. The tiniest movement can define the success and the failure of a component. So VC curves are growing, VC curves are changing with time, and VC curves are being applied in more and more fields of application. And this is also the reason for this webinar, that today we want to perform this webinar to spread the knowledge and make the understanding of these requirements a little bit better. So what is it that we're actually measuring? Vibration can come in many forms. What is it that the vibration criterion curves assume that we should be measuring? In short, in a very quick summary, it is RMS velocity with a spectrum type of the third octave band spectrum between 1 to 80 Hertz. That is the extreme quick summary of what it is that we actually need to be measuring. This is the quantity that we're looking at. But what is velocity? For you that do not know, this is the change in position over time as a vector. Usually, velocity levels can be obtained using a geophone or using an accelerometer and then recalculating the velocity level from that. The criterion, the VC curve criterion, requires you to measure in the vertical and horizontal directions, meaning that a triaxial device is required to be able to be successful in obtaining a velocity signal that you can then apply and look at from VC curves. Now, as we said, we're looking at the RMS velocity. Now, RMS stands for root mean square, right? But it is essentially just a linear average of the level. So this is very important because this introduces a potential error source when comparing two levels. Now imagine you have an application where you're measuring the VC A curve in a hospital with an MRI machine, and sometimes somebody walks by or somebody does something and that creates a peak, vibration peak, that is only there for half a second or 1 second, and then that doesn't happen again. Now it can still lead to the disturbance of that process, of that operation, and still has to be marked. But if we're taking and looking at a very long average, then that very peak will be averaged out because it only occurred once within a specified time window. Martin has a great example in his real VC presentation that he's doing on the actual applications. I think it's very important to know that if you are measuring somewhere where there is a fairly steady state condition, the vibration level is not changing over time too much, then sure, a long integration period can be sufficient because there are no transit occurrences. There is nothing happening randomly. But if you have an event-based scenario where there are peaks, where there are short occurrences, then you must have the ability to have a short integration period, because otherwise you will average out the very level that you're trying to measure. So let's talk a little bit about applying VC curves. A very interesting scenario that we have in a hospital in the US, in California, is a construction that is ongoing inside of a hospital where there is an MRI machine. The MRI machine has been specified to have a level not higher than a VCA and is on a foundation that has somehow been decoupled from the rest of the building, ensuring a good insulation for the vibration. Additionally, there is a requirement that the alarm should be triggered every time an input level, so the level coming from outside of the sphere where the MRI machine is, close to the vibration source, is higher or equal to the level inside of the MRI room, so that we can then start looking at occurrences that were triggered not by a patient walking out from the MRI machine or a technician cleaning or serving it, but whenever we have a higher level at the input of the vibration field, and then we have wherever the machine is. Now, why do we do this? Again, very simple, very simple, very understandable scenario. MRI machines are no cheap equipment, and even though vibration levels don't really destroy them unless very high, they will cause the blurriness of pictures. Now, ask any doctors as you can. The key parameter when it comes to an MRI picture is to have as sharp and a clean image as possible. The difference between a good diagnosis and a failed diagnosis can be the quality of that image. Now, the MRI machine costs money, the technician that operates it costs money, the doctor that then analyzes it costs money. All of this is generating a lot of revenue for the hospital, but anything from patient movement to erroneous magnetic fields within that can affect the quality of that picture, and then will disallow the technician, the doctor, and the patient to perform what they meant to perform. Now, of course, as one of the key parameters when there is some kind of vibration operation within the hospital, external vibrations that are then induced to the MRI machine will also have a huge effect on the quality and sharpness of that image. So in this case study, the floor vibration from outside of the room nearby the MRI machine was measured, but so was the vibration on the decoupled foundation where the MRI machine was put. Now that indicated that we needed to look at short integration periods and look at the third octave band RMS. However, keeping in mind the previously discussed requirement when we have pneumatic and non-pneumatic vibration dampers, we had to define two different curves to be able to successfully measure this. Now, in the 803, which we'll talk a little bit about today, this is possible. So make sure that the hardware you choose allows you to define your own frequency versus amplitude curves so that you can have the ability to change that. In this case study, and obviously Martin is going to talk a little bit more about that as he has the first-hand experience. But in this case study, there was also a multi-point alarm, as we discussed, where we could help to ignore instances where alarms were triggered by the movement of the patient, by the movement of the technician, by people walking around the MRI machine. Obviously, this is not something that is always in a steady state, but thanks to a multi-point alarm system that is implemented in Svantek and can be used with two 803s deployed at two different locations, you can then filter out the occurrences that occur when the output level, so the level at MRI machine, is actually lower than the input level. Also, using Svantek, you are able to do a very easy analysis of these events to make sure that you understand better when these occurred, where they occurred, as well as what kind of levels there were, and if implementing the wave approach, you can even identify visually the type of wave we're looking at. So are they relay waves, are they long waves, etc., etc. So we've now talked about what VC curves are, the origin story of VC curves. We've talked about what kind of studies you can perform with VC curves and what the actual quantity that is being measured is. Now, as the third subject, I'd like to talk about key hardware requirements. Key hardware requirements that you need to have to be successful when performing these kind of sensitive vibration measurement. These come in a point-by-point list. Now, point number one, which obviously is the most important one, is high sensitivity and low internal noise. Now, you need to be sure that you are well below the VC line that you're trying to measure against. Usually, the thumb rule is 3 dB below the VC curve. This means that if your internal noise level is at the VCC level, you can't really be measuring VCC because there is no signal to noise ratio to cover for that. So you'll be triggering that at all times. Now, what we can proudly declare with our SV803 is that we can measure all the way down below VCG, meaning that this system is sufficient enough to measure down to the lowest level. Remember, VCG is appropriate for extremely quiet research spaces, general difficulty to achieve in most instances. That is what Colin Gordon and Associates wrote on that level. Now, the SV803 in its standard setup, without any additional silencers or mufflers or whatever, can reach that level as a VC criterion. So number one, when choosing a system, consider sensitivity and low internal noise of the system. All right, that is number one for me. Number two is something that we're talking about in this presentation, and this is the clear need to be able to have a frequency dependent alarming functionality. This means that it's no longer enough to just look at absolute levels, absolute thresholds. You need to be able to change those in the frequency domain. As VC curves show us, even though them being quite well defined and not really complex in their understanding when comparing to other ground vibration standards, it is still possible that you will have to change them from being curved to being flat and back. So you need to have the functionality of alarming and marking whenever levels are changing as a function of frequency. Flexibility and short integration settings. As we mentioned, if you are measuring a scenario where you have transient vibrations, where you have sudden changes in levels and there is no steady state, you need to be able to have a short integration period, or you risk missing whatever it is that you're trying to measure. If you have an integration period of 30 seconds and you are just looking after sudden peaks, that peak will lose a lot of its magnitude because of being averaged out over a too long period. So you need to have hardware that can both do short and long integrations depending on whatever it is you want to measure. The fourth thing that I want to talk about is in-device analysis and class 1 filtering. A very neat thing with VC curves that we can't really say for BS or DIN standard is the fact that they are based on third octave band filters. Third octave band filters are standardized. Third octave band filters have classes of accuracy. Thanks to that, we can be sure that if you're measuring velocity in the States and you're applying a third octave band filter, and you will be measuring the same level in Australia, in the UK, or in Sweden, you should have the same frequency domain signal. So you should have the ability to transform the time signal to frequency domain and still have the same levels that you would in any other country. We all know that in this when performing the frequency the FFT, we can choose everything from the windowing functions, from bin sizes, from overlappings, etc., etc. All of that will affect the way the result will look, even though the time signal is the same. Now, thanks to third octave band, we can have the same level everywhere. Now, what do we mean by in-device analysis? A lot of semiconductor plants will have extremely stringent requirements, not only when coming to vibration, but also when talking about the security and privacy within the plant. Now, a lot of semiconductor clients that we have will not allow any type of cloud-based analysis or cloud-based communication with the device. If you then have a device that is based on a cloud analysis before it can make a conclusion whether something exceeded or not the level, then you can't really be targeting these clients, because you will find that in a lot of these clients. Any kind of wireless communication with a cloud server that is outside of their jurisdiction is a big no. Because of that, the analysis must be done by the integrated analyzer, so the DSP inside of the device, so that you can do an offline analysis that then allows you to see whether you are passing the vibration criterions or not. And the fifth and last thing that I want to talk about is the ability to perform a field calibration and sensitivity check. Now, when we're looking at these kind of low levels, these kind of fine applications, then everything is of interest. We need to be able to see that we have the exact same sensitivity of the geophones that we used to have, because even a slight drift in the calibration gain can affect if you're able to perform a good analysis or not. Remember, we're checking against something, right? So let's take again the semiconductor business. Let's say that we deploy a device that is supposed to measure the vibration at an inspection stand where you have these very high level microscopes. The technicians or people manning these will be able to tell if it's blurry or not. But if your device deployed out there shows levels well below VCC while they are complaining on these levels, then that means that perhaps your calibration factor on your geophones is not up to date. This is why, per ISO 8041, it is highly advantageous to be able to perform an in situ field calibration the same way you would with a microphone and acoustic calibrator. The good news is that us here at Svantek have developed an instrument perfect for all of these applications. We're talking about an extremely high sensitivity and low internal noise of the device in its standard form. We're talking about very flexible frequency dependent alarm functions where you can have up to 3 different vibration frequency curves for vibration thresholds. We're talking about flexibility and in integration where you can go all the way down into 1 second when it comes to both FFT and third octave band spectrum integration. We're talking about in-device analysis and class 1 filtering for the octave bands. And finally, a cheap and easy way to field calibrate the SV803 geophones simply using a handheld calibrator such as the SV110. So that is all when it comes to plugging off the products. Thank you very much for my part. And now I will be turning over to Mr. Martin. Martin, thank you very much. Over to you, sir.
Okay, thanks very much. Okay, is that coming through okay, Adam?
Yeah, I can see it fine. Thank you.
Great stuff. Okay. Right, well, hello everyone. So I'm going to talk about application of VC curves, and by default, that generally lends itself to science and research facilities. Right. Okay, so a quick introduction to the team. So I lead the vibroacoustics, the vibration and vibroacoustics team. I'm based in Manchester. We do a lot of work down in London, and we also span continents as well. So we have people located in Spain as well. So we're a small team. We're very, very busy. So busy that we're actually looking for people as well. So by the end of this, you feel like this is the type of thing that you'd like to do, give us a shout. Emails at the bottom. So yeah, plugged on. Let's crack on. So yeah, so vibration in science and research schemes. What's most interesting about science and research schemes is that vibration really is top of the bill.
It's not an afterthought, as is the case in quite a lot of acoustic consultancy design projects. It's top of the list, mainly because the end user requirements and the tools and the scientific equipment they need to use are so vibration sensitive. So that ultimately drives the end user specification and puts vibration in from the very outset. In these ultra low vibration facilities, where we have levels of vibration far below the level of perception, it's not just environmental vibration that actually affects the end result. It's a combination of everything. So that could be MEP, noise, if there's any noise generating activities, and also footfall, users walking around the complex as well. So that becomes a very detailed assessment, and it's quite a holistic form of assessment, design challenge that vibration presents in these science and research facilities. And because of that, there's a high level of coordination that's required. So you first have to get an understanding from the client to see what actual vibration limits are specific to their facilities. And then how does that affect the structural design? How's that going to affect the building services design? How's it going to affect movement through the building? So you can sort of see when you start to build in all these different parameters, vibration is very important. And in order to get, these things come with a price. If we're going to start to influence structural design, we need to be pretty sure what we're up against from the outset. And for that reason, measurement forms a key aspect, and the sooner we get it done, the better. And to sort of zoom out of that and say, how does that affect the role of a vibration consultant? Well, it's not just a measurement at stage one, and then that's it. We just report and disappear and move into other projects. There are actually things to do throughout the whole of the construction phase of a building that affects the clients, the end users. We work with the architects, structures, and MEP. And I suppose the role of a vibration consultant, what's probably most unusual compared to roles of an acoustic consultant, is we deal with structures a little bit more. So, I mean, we've had a great overview of the VC criterion curves, obviously rooted in the history of Colin Gordon and Eric Ungar. And as was said, it's an RMS velocity value used to classify levels of vibration. The guidance, the accompanying table, which goes alongside these curves, does say that VCE, anything greater than VCE, and by greater I mean the VCF and the VCG, is for assessment only. That table is quite old actually, and it's not uncommon for science and research schemes to actually be designed to levels lower than this. So VCF and VCG have and do continue to be used as basis of design for modern day, very sensitive science and research facilities. And so this is the table that accompanies the VC curves. So, and one of the things that you will, notice is that, they, as you go increase alphabetically, the amplitude becomes more and more tighter, more onerous. And it's also, generally speaking, a halving of vibration level as well. So you can see the VCB is half of VCA and VCG is half of VCF. So that's an important thing to keep in mind as we go through. And as we say, these VCFs and VCG levels of vibration have actually formed a design criterion for schemes that we work on today. And it's an honourable mention for structural engineers and how VC criteria affect structural design. Now, the common language for a structural engineer is to speak in terms of response factor. Response factors are a means of describing floor serviceability, how the floor feels under footfall excitation. And response factors are actually based on acceleration that's weighted to the perception of human perception to vibration, in a similar way that we would weight noise levels to better replicate the perception of human hearing. A response factor is a dimensionless score, if you like, so there's no units assigned to it, but a response factor of 1 would say just about perceptible to most of the human population. A response factor of 2 will be twice the amplitude of vibration to response factor 1. Now, VC curves, if you were going to apply that rationality, VC curve, the VCA is probably analogous to a response factor of 0.5. And by that very definition is below the range of perception in humans. So as we go down the VC curves, you'll have fractions of 1. It's not that it's fine for structural engineers to convey the message of how a scheme, a science and research scheme, will respond to footfall, But from a holistic point of view, or when we're quantifying measurements, it's not something that we tend to go to. So VC curves can and do remain the metric of choice. And moving into sort of how we quantify this, how we do our measurements, how we start to think about things, there are some standards that do give advice on measurement and coupling, and one does tend to reference the other. And you can read those there here if you want to go and have a look. But I mean, the key considerations, as we've seen in the previous presentation, we talk about sensor selection and how capable it is of capturing the levels of vibration that we are interested in, but also how we couple it to the ground, the metrics that we choose, and how we can post-process that data to get a meaningful result with the design criterion that we're interested in. And yeah, so I mean, when we talk about measurements, from my point of view, a measurement isn't something that we just do at stage 0. It's usually an iterative approach, but most projects begin with some kind of a scoping assessment. From the scoping point of view, we usually just put accelerometers down on the ground or in the soil, and that dictates how we might couple. So we may need a ground spike in the soil, but we generally hope for a nice flat hard surface to get a clean measurement upon. As I said before, the VC range is in the third octave bands, 1 to 80 hertz, and it's absolutely vital if we're going to be in these sort of lower VC regions that we have high sensitivity devices to capture that level of vibration. We do, as you might do with a noise survey, you wouldn't just measure one location. The vibration is even more important for a number of reasons. The soil parameters and the ground conditions can vary over the course of meters. We've had experience of measuring vibration in location A, and then like location B within 12 meters has been 10 dB greater. And it's not until you start to do borehole excavations or different types of measurements where you get into the ground that you start to appreciate what's going on. So if you're not mapping these areas, then there's a good chance that you might miss it. And it's also important to note that there's more than one vibration wave type that we might be interested in. So some sort of classic wave types are on the right. There's not all of them. There are many more. But a particularly interesting one is the Rayleigh wave. With the P waves and the S waves tend to be body waves. So by that, what we mean is that the whole medium is engaged, and you could measure at one point in it, and it wouldn't vary too much with depth. That's not the case with Rayleigh waves. It's a surface wave, and you can see from the schematic here that it kind of decreases with depth. And that does have some implications, because some science and research facilities are below ground. So you might find you'll get a better response at a below ground location than you would up on the surface. So from the outset, if you're trying to scope these places out, it's important to know, have an understanding of what you might expect in terms of wave types. And as was mentioned before, the integration period plays a key factor into what VC curve you might end up with. So obviously the averaging, by this we mean the integration period averaging. So here we've got 3 curves. We have a 1 second rolling RMS value. That's the pinky one, which tends to have be a bit more hairy in terms of its appearance. That's because it's got a finer resolution in terms of time history. And then we also have a 10-second RMS and a 30-second RMS. And it comes as no surprise that the 30-second one has lower peaks than the 10, and the 10 has lower peaks than the 1 second RMS. And what does that mean when we look at sort of max values? So you can see there's a clear peak in the response, somewhere in between 500 and 600 seconds. And that's presented in the table that you can see there now. Now, I've presented it in a few ways. So it's all these ratios and level difference columns are with respect to the 1 second time history. So for the 10-second case, you can see that the ratio, if we just divide the velocity, linear velocity meters per second, one over the other, you can see that the 10 seconds actually about 70%. The peak at that point between 500 and 600 seconds, it's about 70% of the 1 second RMS. The 30-second equivalent, however, is about 0.5. And if you recall from the table that we showed before, VC curves tend to shift, they double or half depending which way you're going. So that could actually be an important thing that is missed if you have an integration period that doesn't capture the time varying nature of the environment that you're in. So it's important to keep an eye on that. And maybe one way to get around that is to present results as a range of statistical values, and that could include anything depending on how you're trying to present your information to the client. It could be a max mean, some kind of mean plus standard deviation, or percentile values. And percentile values is what we've got in the figure on the right. So you can see that it's quite a low level of vibration, this particular measurement location, with the means well below VCG. But actually the 99th percentile sits just somewhere below VCE. And the maximum, that was the band maximum, so the highest value that any third octave band took over the course of the survey period was over VCA. Now that's, that reporting the maximum in of itself might be the end of the project if we were to just rely on that particular piece of information. However, the context of the statistical analysis, the 99th percentile, would say, well, okay, there's no, for 99% of the time it was below VCE. That may have been okay. It gives you an opportunity to discuss this with the client and identify any outliers that may well have been me falling into the vibration meter at the time. Who knows? But it seems atypical to the general response. Okay, so as we said at the beginning, the measurement of environmental vibration is not where the fun stops. There's lots of other things to consider. So we've got MEP sources, which are generally a big ticket item in terms of controlling vibration, especially when we're looking at facilities that are in the region of VCE to VCG. Is very important because the scales and the sensitivities are so great. The effect of construction is quite important too, not just in terms of construction that the creation of a facility might occur, because sometimes these areas are already in science regions, science parks, science campuses. So how the construction of that might affect other operations nearby. We've dealt with projects in the past where we've had to really get hold of a construction program and essentially, curtail that construction program to make sure that certain limits didn't affect mass spectrometers in this instance in a scheme that was affected by this. An understanding of how the vibration can propagate through a structure. So that's kind of the plot on the right. For that, we tend to use numerical modeling software to best analyze that, because when we're looking in the regions of 1 to 80 Hertz, we are really looking at like modal responses of buildings, and we have to be very careful that the levels that we predict off the back of our vibration measurements are bespoke to the structure that we're interested in, because the implications are quite big if we're going to start to talk about concrete and cone spacings and so on and so forth. And it's not just an excuse to have a fancy infographic of someone with a slam ball, but we have actually had experiences of amenity spaces within commercial science and research facilities, semiconductor plants or places where there's lots of activity, day and night, do like to look after their staff. They are homes from home really for a lot of people that work there. And as a result, they do have facilities and they do have gymnasiums and things like that. So it's important to ensure that that's covered as well. So there's lots of things to consider as part of these facilities that you might not ordinarily think. Okay, yeah, so hopefully that's a bit of a whistle-stop tour, but just an overview of the type of things to expect and to be mindful of when thinking about these levels of vibration in SNR facilities, and also facilities that require a very low level of vibration amplitude, such as like hospitals and the like. So they do require high quality vibration measurements, high quality design. All of the decisions that are made from these measurements, in this low frequency range does affect users. It affects how they might be able to go about their job. It affects the spaces, the sizes, and more importantly, the devices. More's the case. And actually, having this measurement doesn't stop there. There's interesting things to do and challenging things to do throughout all the rebus stages. And VC curves are the industry standard, but bear in mind they do require some context when applying them. So ensure that your metrics and your client discussions and your measurements, importantly, are correct. And the good vibration dyne includes all sorts of vibration, not just environmental, but also internal too. So thanks very much for your time. Emails at the bottom if you'd like to get in touch.
Thank you, Martin. Really appreciate it. Great presentation, and thanks, Adam, as well. I know that you've both put in a huge amount of time and effort. We really appreciate it. Thanks to everybody that's joined the webinar today, and for all of those watching offline. If anybody has any questions for Martin or Adam, then just email into sales@svantek.co.uk. But that's it from us today. I hope you found it interesting, and please look out for future content from us. There's more coming soon, and yeah, hope to see you all very soon. Thanks very much.